Okay, welcome back to operations research and LP formulation or transportation problem. So the last video ended with this one having a mistake. So I now corrected the mistake. Let's hope that this was the only place where the mistake was. We have to make more corrections if that is the case. I decided not to delete this babbling with this mistake because this is indeed the case where it's easy to make a mistake. So I think it's educational to show you this. So what is our objective function? So this is somehow easy, at least for me to read, because these are the Cij is the cost from I to j, Xij is the amount from I to j, then the total cost is we just sum up I and sum up j. And now in this particular case we have C like this, so we actually will have 6 numbers and 6 variables, and they have to be written in the correct form here. So what do we have? So these first 3 are from the first source to the 3 different destinations we have. Okay, so these will be x11, x12, x13. Okay, and these are from the second source to the first, second and third destination. So these will be x21, x22 and x23, and let's see are they correct. This is x11, yes. 4 has x12, 6 has x13. All right, then we have the 2's. x2, 1 is 5, x or has the coefficient, and this is x22 has a coefficient 7 and x23 has a coefficient 5. Okay, now they are correct. So this is the kind of, it's not too complicated otherwise, but it's a matter of bookkeeping, which is sometimes tedious, and of course later we will leave this for the computer to do. All right, so now we know the decision variables and we know the objective function. What is the next? The constraints. So what are the constraints we have in this problem? And maybe this betrays the constraints. So this was the costs. So the objective function capital C here defines that, and the constraints are, yes, they are here supply and here demand. I mean that's the rest of the data, we should use it somewhere, so maybe it's the constraints that we use. And there are indeed 2 kind of constraints. There are supply constraints, sorry about this painting, and demand constraints. So what are they? So here, let us talk about the supply side first. So each source, so we have 2 sources, they were the Arrakis and Tleilax, so they only have so many megatons of spice. So obviously you cannot transport from them the more that there is. So this gives us a constraint, or actually 2 constraints, upper bounds. And in general transportation problem, each source will have a constraint associated with it, saying that from that source you cannot transport more than there is. All right. So these are called the supply constraints. And a way of mathematically writing them is, this may look again fancy, but if you think about it, this simply says that, so Xij is the amount of stuff that flows from I to j, and if I sum over j, because Xij is from I to some particular j, and then the other j's, if I sum up from all the j's, this tells us how much there is stuff leaving from the source I. So in this formula, this side does not depend on j because the j is summed over. So this is just some number depending on I. And this number, sum over the xij's, is the number of spice that flows from the source I. And this must be less than equal to, well, the amount there is, obviously. And this is just constraint for the fixed I, and then, yes, maybe I should have even bold-faced it. This is for all the sources I. So we have as many supply constraints as there are sources. All right. And again, I should have maybe pointed this out earlier. So maybe it's a bit unfortunate this SI is now used for the source or supply. We used it earlier, this S, to denote slack variables. Now it has a different meaning. I'm sorry about this clashing notation. I hope it doesn't cause confusion. I of course could have used different names for the variables, but this is also something that you should get used to it. Sometimes the same notation is used for a different meaning, and well, that's the way things usually are, so you should get used to it. So I'm sorry for the whole operations research community that this is the case. All right, that was a little bit of side note. So this is the general form of supply constraints that's always there. It's like this for all transportation problems. So let us now look how it looks in this special case of spice transportation. So we have two sources. We had the source Arrakis and the source Tleilax. They had 15 and 20 availability. So these constraints here, we have two constraints and they are given here. So let me go back here. So let's see, the Arrakis was 3, 4 and 6. They are less than 15 megatons. So actually these numbers don't play any role now. So it's just 15 and 20. And the point that Arrakis was the source 1 and Tleilax was source 2. And supply 1 was 15 and supply 2 is 20. So this is what we have there. So x11 is the how much there is from source 1 to going to port 1, x12 how much there is from source 1 to port or destination 2, and x13 is how much there is flowing from source 1 to destination 3, and there are no more destinations, so this sum tells us how much there is flowing from source 1 to wherever it flows, and this cannot exceed 15 because 15 is the supply there is. And let me really now check that this is correct, the indices. So always first one and then the destinations run through 1 to 3. And similarly here, this is now x2, something will be what is flows from source 2, and source 2 was a Tleilax and it had supply 20. Okay, so here we have it. These are the supply constraints for our problem. There are two of them because there are two sources. Okay, and then we have also destination constraints. So this is like the supply constraints, but of course the other way around. So each destination, it demands so many megatons of spice. And according to the problem, we are committed to meet these demands. So if dj is the demand for spice in the destination number j, we have the demand constraints in general form like this. So now it goes really the other way around, and you should just look that the i's and j's are switched around. The idea that now we are not looking at each source, but we are looking at each destination. And like this was the amount that flows from I to anywhere, this is this anywhere is now the other way around is j. So sum over I xij, this is the inflow. How much there is flow going from different sources I, that's summing up all I, to the destination that is a fixed j. And this must be at least dj, that is the demand. We have promised that much to the destination j. So this is just like here, but i's and j's goes the other way around, and of course it's now a lower bound, not an upper bound. And I hope that now, like this, then these are quite clear. So x1, 1, 2, 1, this is the inflow to the destination 1. And let us go back here to see why it's 17. The 17 is this number here, that's the demand. So then the 8 megaton, that's the demand for the destination 2. Let's check that this is okay also. So this is from 1 to 2 and this is from 2 to 2. And there are no other sources than 2, that has to be at least 8. Okay. And finally the 10 there, 10 is the demand of Giedi prime. Giedi prime had the index 3. And yes. So from 1 to 3 and 2 to 3 must be at least 10. So that's pretty much the modeling part. Again, we should remember the sign constraints. So xij must be bigger than or equal to 0. Again, it was not explicitly stated in the problem, but I mean, probably it's obvious, because if they would be negative, it would mean that we transport negative number of some amount over a route, and maybe in some sci-fi novel it would mean antimatter or something like that, but let's not go there. It's kind of relatively obvious that in our case we cannot think about transporting negative amounts. It doesn't make sense, at least not in this context. Alright, then finally I have simply written this down in this special case. So this xij is bigger than or equal to 0 for all I and all j. So here I just listed them for kind of completeness purposes, just to point out that there are actually 6 of these decision variables. They are just written in a 2 by 3 matrix, so 2 rows and 3 columns. And so let us see what we have found out. So we have actually found out that our problem 9.1, let us have it here. So this kind of problem that was written in a legal way, represented as a picture, and then, which is maybe the most convenient for us, this kind of a table where we have transportation costs, supplies and demands. This will be as an LP the following. So this, yeah, it kind of hurts the eyes, doesn't it? But this is what it is. So what I did simply in this 9.3, I collected, so here is the objective function. These 2 upper bounds are the supply constraints, these 3 lower bounds are the demand constraints, and finally I have just listed the sign constraints, and all of them has to be non-negative. And one thing about to notice here, and this is important from the implementation point of view, when we want to implement this with GNU Octave and solve it with GLPK, is that while these x1 and x2 and so on, they form a matrix, now what I happened here is that I put this in the kind of standard LP form, or the normal LP form. It's not standard because there are lower bounds here and upper bounds here, and it's even a minimization, but in the form that we have seen LPs, where the variables are all in their own column. So here you see x1's are own column, x1's 2's have their own columns. Same for x 1 3, and then I start 2 1 2 2 and 2 3. So now this is something that is related to the remark we had about the price to pay for the cleverness of having matrix formulation for the decision variables. And also this has now somehow tells us that this technology matrix is the pain in the head to construct, because somehow the objective here, these numbers come from the cost metrics. See, they are there more or less. Also these bounds here, so these are the supplies and here are the demands. Okay, these supplies are upper bounds and demands are lower bounds, but that's not a big deal, that's easy to implement. But yeah, here, this technology matrix, okay, these are sign constraints, they are not proper either, but this here, the technology matrix, this is yeah, that's a bit tedious thing to do. And indeed, let me put this slightly bigger here and end this video lecture here, so you will have this picture burned into your retinae. And what to do with this will be the topic of next video lecture. See you there. Bye.